Right now, it's inside the orbit of Jupiter and is headed for its closest pass to the Sun at the end of October. That's going to be barely inside the orbit of Mars, and then it's going to keep going on its way out of the solar system.
3. I/ATLAS didn't announce itself quietly. When it blazed into our solar system at over 130,000 miles per hour, it brought with it chemistry that shouldn't exist and behavior that's forcing scientists to question everything we know about interstellar visitors. The James Webb Space Telescope just revealed it's wrapped in a carbon dioxide fog so thick it's unlike any comet we've ever seen. But that's not the strangest part. The tale that breaks the rules. From the very beginning, something about 3 I/ATLAS didn't sit right with the scientists watching it. It wasn't just that the object was fast or interstellar. It was the way it behaved once it got close enough to be seen clearly.
This object has just been discovered. 3I Atlas was discovered on July 1st by the NASA-funded Atlas survey.
When the Hubble Space Telescope locked onto the object and began sending back high-resolution images, the data didn't reveal a tail stretching out behind it. Instead, it showed something no one expected. A plume aimed toward the Sun, bright and oddly shaped, pointing in the exact opposite direction from where it should. Normally, comets develop long tails that stretch away from the Sun as solar radiation and wind force particles off the surface and into space. It's a simple, well-understood mechanism. Sunlight heats the comet, volatile ices vaporize, and dust is carried away in the flow, pushed outward like smoke in a breeze. But in this case, the plume wasn't trailing behind. It was facing forward, aimed directly at the Sun. And it held that position with alarming consistency.
4 images, this is a brand new near-Earth asteroid.
Across multiple observatories, Hubble in orbit, Gemini South in Chile, and Lowell Discovery in Arizona, the same feature appeared over and over again. The plume stayed narrow, focused, and sun-facing, even as viewing angles and exposure times shifted. It wasn't faint or fleeting either. It was sharp, well-defined, and bright enough to be picked up in every frame. And then came Hubble's July 21, 2025 observation, when the telescope imaged 3 I/ATLAS at a distance of 277 million miles from Earth. The result was a teardrop-shaped cocoon of dust wrapped around the object, a structure that didn't look like any ordinary comet tail. NASA itself described it as unusual, a cloud that seemed to envelop and push outward at the same time. What made things even stranger was that this forward-facing plume didn't just appear in one wavelength.
We'll pick out objects that are moving inside of the 4 frames, and we have to identify if they are real or if they are false detections.
Instruments measuring in infrared, visible light, and even ultraviolet confirmed the same structure. The consistency across instruments ruled out sensor errors or exposure artifacts. And the brightness level wasn't just visual noise. It crossed thresholds that allowed researchers to extract chemical signatures and motion vectors with confidence. Its behavior defied the basic rules of how particles should react under pressure from solar radiation. Astronomers began describing it as blobby, an informal word that somehow fit the stubborn, asymmetric arc they were seeing. The plume wasn't a symmetrical jet, and it didn't curve the way comet outgassing typically does. It also didn't fade or drift over time the way you'd expect if it were just dust reacting to sunlight. It looked thick, and that direction, always pointing toward the Sun, was the one thing physics said should be impossible. Researchers ran simulations using standard comet models, tweaking dust particle sizes, adjusting gas release velocities, and accounting for solar wind conditions. But nothing lined up. The models failed to produce a plume that would face the Sun, let alone one that would stay locked in that direction for days.
We've only discovered less than 40% of the 90% of the object we need to discover.
The solar wind should have blown that dust away, scattered it into a tail, and erased the plume completely. But the object kept pushing back. It refused to behave. NASA didn't use the word propulsion, but during press briefings and in public statements, the agency did something rare. They asked an open question. They asked the world to look at the same images, study the same plume, and answer something that shouldn't need asking. What force could possibly drive dust toward the sun? A propulsion analogy that's hard to ignore. As more data poured in and the plume refused to behave like a normal comet tail, comparisons began to surface. Most astronomers stressed that the feature was unusual, but still likely natural.
From images, we also saw that this object is active, which is an indication that this object is in fact a comet.
Yet a smaller group of researchers saw something else, patterns that felt eerily familiar. Among them was Harvard astrophysicist Avi Loeb, who pointed out details that set 3I/ATLAS apart. Loeb noted that the plume didn't just point toward the sun, it held its shape in a way that looked engineered, narrow, collimated, and persistent. To him, it resembled the exhaust of an ion thruster. Ion propulsion isn't speculative. It's a technology used by real spacecraft, launched by NASA, ESA, and other agencies. Instead of burning fuel in a chaotic blast like chemical rockets, ion drives accelerate charged particles with electric fields. The particles stream out in a thin, focused beam, producing very little thrust in the short term, but sustaining it for months or years. That's how NASA's Dawn spacecraft navigated to the asteroids Vesta and Ceres, and why engineers consider ion drives the key to future deep space travel. What drew attention was the contrast with how comets usually behave.
2023 DZ2 was a significant asteroid. A rock that size might only happen a handful of times per century.
A typical comet outburst produces a wide fan of material, messy, uneven, with particles of different sizes scattering in all directions. But 3I/ATLAS didn't fan out. It didn't fade. Its plume looked like a beam, a steady push of heavy material pointing precisely against its direction of travel. Orbital mechanics make this even stranger. Perihelion, the closest point to the sun, is where objects move fastest and where energy has the greatest leverage. Engineers call it the Oberth effect. Fire engines here, and the thrust multiplies, giving you far more efficiency than anywhere else in your orbit. If 3I/ATLAS were somehow trying to adjust its speed after crossing interstellar space, this would be the perfect time.
The physical makeup of an object tells us about its capability, its impact potential. What can it do on the Earth?
No dataset confirms that this is a spacecraft, and no official body has drawn that conclusion. The dominant view is still that this is a comet behaving in strange but natural ways. Yet the chemistry adds another layer of curiosity. The plume is rich in carbon dioxide and shows traces of nickel. Both can be ionized under the right conditions and, at least in theory, could mimic propulsion. There's no xenon, the propellant used in most ion engines, but that doesn't end the analogy. Instead, it raises a harder question. Can a natural process really imitate propulsion this precisely, or is that resemblance too close to be chance? Chemistry that shouldn't exist.
At a velocity of about 135,000 miles per hour, so it's going really fast. For that distance from the sun, this is really exceptional.
By the time the James Webb Space Telescope trained its instruments on 3I/ATLAS, expectations were already high. Webb's infrared eyes are among the most powerful tools in space, capable of breaking down the light from distant objects into detailed chemical fingerprints. And yet, what it revealed didn't confirm existing theories. It crushed them. The most shocking detail came from a simple ratio: carbon dioxide to water vapor. In nearly every comet studied to date, from the Kuiper Belt to the Oort cloud, that ratio falls between 0.1 and 2. Some are colder, some are more active. Webb detected nickel in the sunward plume, a known component of rocky bodies and often seen in comet tails. But there was no iron. That pairing, nickel and iron, usually shows up together because they form under the same planetary conditions and exist side by side in most cosmic environments. It's chemically bizarre. and there's no simple reason for it to happen in nature.
Observing this rare comet that had water vapor in it.
The composition of the plume added to the mystery. These unusual materials, high carbon dioxide, bright nickel, low iron, were not located in the trailing tail, where you'd expect heavier particles to settle. They were concentrated in the sunward plume, the very jet that defied solar pressure and aimed directly at the sun. The materials that should behave like dust were pushing against radiation, while the typical gases, like carbon monoxide, were found in abnormally low quantities, especially for something moving at interstellar speeds. If nickel is present, iron should logically appear alongside it, unless the temperature required to release iron had not yet been reached, or the object itself is chemically unstable. Either possibility is problematic. If the temperature threshold was the issue, then the question becomes why carbon dioxide, which also requires heat to sublimate, was released so early and in such high quantities. If the comet is chemically unbalanced, then its structure and origin fall even further outside the known categories of planetary formation. The chemical profile of 3E/A-TLAS, from its ice-to-gas ratio to its missing metals to the plume's unnatural composition, doesn't match anything from our own solar system. It points to a birth far beyond any warm star, in a region of space so cold and so alien that even our best models fail to simulate its conditions. A place we may not even have mapped yet. Nickel without iron. When the James Webb Space Telescope trained its infrared eyes on 3I/ATLAS, it didn't just find unusual chemistry, it found impossible chemistry.
It is only the third time we have detected an object that has come from beyond our solar system.
The carbon dioxide levels were off the charts. There was cyanide in the mix, and the nickel-to-iron ratio defied everything we know about how cosmic objects form. The most shocking detail came from a simple ratio, carbon dioxide to water vapor. In nearly every comet studied to date, from the Kuiper Belt to the Oort cloud, that ratio falls between 0.1 and 2. Some are colder, some are more active. Webb detected nickel in the sunward plume, a known component of rocky bodies and often seen in comet tails. But there was no iron. That pairing, nickel and iron, usually shows up together because they form under the same planetary conditions and exist side by side in most cosmic environments. It's chemically bizarre, and there's no simple reason for it to happen in nature.
From a place called the thick disk, full of ancient stars.
The composition of the plume added to the mystery. These unusual materials, high carbon dioxide, bright nickel, low iron, were not located in the trailing tail, where you'd expect heavier particles to settle. They were concentrated in the sunward plume, the very jet that defied solar pressure and aimed directly at the sun. The materials that should behave like dust were pushing against radiation, while the typical gases, like carbon monoxide, were found in abnormally low quantities.
Dust being pushed back behind the object by the solar radiation pressure.
Especially for something moving at interstellar speeds. The Very Large Telescope has also shown that 3I/ATLAS is emitting cyanide, a discovery that makes its chemical fingerprint even harder to classify. If nickel is present, iron should logically appear alongside it, unless the temperature required to release iron had not yet been reached, or the object itself is chemically unstable. Either possibility is problematic. If the temperature threshold was the issue, then the question becomes why carbon dioxide, which also requires heat to sublimate, was released so early and in such high quantities. If the comet is chemically unbalanced, then its structure and origin fall even further outside the known categories of planetary formation. The chemical profile of 3I/ATLAS, from its ice-to-gas ratio to its missing metals to the plume's unnatural composition, doesn't match anything from our own solar system. It points to a birth far beyond any warm star.
The trajectory is very well aligned with the planets, and it will come very close.
In a region of space so cold and so alien that even our best models fail to simulate its conditions. NASA's SphereX spacecraft has since confirmed that it is the largest and brightest known interstellar visitor to our solar system, a place we may not even have mapped yet. Non-gravitational acceleration. No matter how strange an object looks, scientists always come back to one question: how does it move? In the vacuum of space, motion reveals more than images ever can. And when researchers started tracking the path of 3I/ATLAS through our solar system, what they saw didn't add up. At first glance, the comet's orbit seemed typical for an interstellar object, a steep hyperbolic curve, inbound from deep space and slingshotting around the sun before heading back out.
Good amount of data, more than 100 observations. We know its trajectory fairly well.
But over time, something odd appeared. Atlas wasn't following the exact trajectory gravity alone would predict. It was drifting, ever so slightly, in a direction that made no immediate sense, toward the sun. This tiny, persistent deviation sent researchers back to their models, and when they reran the math, they had to add a new term: a sunward acceleration of about 4 × 10 to the -7th meters per second squared. To a layperson, that number might seem laughably small, less than a fraction of a feather's weight. But in space, even the faintest push matters. That tiny force, applied consistently, translates into a deviation of thousands of kilometers over the course of the comet's journey.
55 million light years away. That thing is around 6 billion times.
Suddenly, what looked like a negligible effect became an undeniable sign that something unusual was at play. Here's what made it even weirder. The direction of that push lined up perfectly with the strange sun-facing plume captured by telescopes like Hubble and Gemini South. So not only was Atlas breaking the usual shape rules for a comet's tail, now it was breaking the motion rules too. If this sounds familiar, it should. This is exactly what happened with Oumuamua in 2017. That object, too, showed unexplained acceleration, and no one could agree on what caused it. Some blamed icy outgassing. Others claimed structural flexibility or unknown physics.
Oumuamua is apparently very long and narrow, with an axis ratio of about 10:1.
But no comet model at the time could recreate the push without resorting to extreme, unverified forces. With 3I/ATLAS, it's happening again. But this time, the alignment between plume direction and movement shift is even more precise. That's why some researchers, like Avi Loeb, began revisiting a controversial idea. Maybe we're not looking at natural jets of gas and dust. Chemical analyses have already shown unusual compositions in Atlas's emissions, signatures that don't fully match known cometary outgassing. Put that together with the perfectly aligned plume and the calculated sunward acceleration, and the mystery deepens. Maybe we're not seeing random chemical vents at all, generated by focused material ejection, the same principle behind propulsion. The precision flyby. If the plume was strange and the push was measurable, then the flight path of 3I/ATLAS is something else entirely. Because when you look at where it went and how precisely it went there, one thing becomes clear. This object didn't just wander into the solar system, it threaded a needle. 3I/ATLAS is flying in a retrograde orbit, meaning it's moving opposite to the direction of most planets. That's already rare, but its path is tilted at just 5 degrees off Earth's orbital plane.
Everything in the solar system is either on a circular or an elliptical orbit,
practically skimming across the same flat disk that holds all our major planets. That's like tossing a dart across a room and watching it sail perfectly level between shelves of spinning plates. Astronomers ran simulations to model the flyby, and what they found was more than coincidence. In a matter of weeks, 3I/ATLAS would pass within 29 million kilometers of Mars on October 3, 2025, 97 million kilometers from Venus, and 54 million kilometers from Jupiter. 3 planets, 1 object, all in a single inbound arc. Those aren't near misses. Those are close calls on an astronomical scale. So scientists did the math. The probability of such a multi-planet flyby is less than 1 in 20,000. Even more telling is its eccentricity, a measure of how stretched or non-circular its orbit is. Most comets have slightly curved paths, but 3I/A TLAS has an eccentricity of 6.141, one of the highest ever recorded. That's not a curve, that's a line, a straight shot through the system. Orbital dynamicists, the folks who spend their lives tracking objects in space, began calling the trajectory surgical. It means something precise, calculated, deliberate. Even planetary defense teams, the ones usually on the lookout for extinction-level threats, started watching, because its approach was too perfect to ignore. There are natural explanations, of course. Maybe it's all just a string of cosmic luck. Maybe this is what happens when you run billions of simulations and wait long enough, once in a while, one object hits the bullseye. But when you line up the odds, the angles, and the near-planet encounters, it's hard not to believe that this was designed. Perihelion, the blind spot. On October 30, 2025, 3I/ATLAS will disappear from view. Not because it's gone, but because the sun will swallow it from our perspective. This is what astronomers call a solar conjunction, a period when an object slips behind the sun as seen from Earth. The effect is blinding. The overwhelming brightness of our star drowns out the faint signals of whatever passes behind it. During this time, no ground-based telescope will be able to track 3I/ATLAS. Even space-based observatories like Hubble or James Webb face the same limitation. Their instruments simply can't see through the sun's glare. Radar won't help either, leaving astronomers unable to confirm the comet's position, speed, or activity for weeks. This isn't unusual. Many objects vanish briefly during their orbits around the sun. But with 3I/ATLAS, the blackout carries extra weight. If anything about its behavior were to change its speed, its angle, its shape, or that strange sun-facing plume, this is the window when it could happen unseen. Observing campaigns are being timed to pick up the comet as soon as it re-emerges from behind the sun. The reasoning is simple. If something shifts, it won't be while we're watching. It'll be while we're blind. For an ordinary comet, this wouldn't matter. They loop around the sun, shed some dust and gas, and move on. But 3I/ATLAS is no ordinary comet. It carries a plume physics can't explain, chemical signatures that don't match normal ratios, and an orbital path that has already raised eyebrows. Now it's heading into a perfect window of invisibility, and whatever happens in that shadowed moment will remain hidden until it returns.
This is something that we didn't realize before, and they also move without creating an exhaust.
The bigger pattern. What's happening with 3I/ATLAS isn't random, and it isn't new. It fits into a growing sequence of interstellar visitors that began less than a decade ago, but its implications reach far further. In 2017 came Oumuamua, the first object we ever confirmed from another star. It looked nothing like a comet, carried no tail, and yet it accelerated as if something invisible was pushing it. 2 years later, in 2019, came Comet Borisov. This time the structure was clear, an active comet with a long tail, but the chemistry was off, with signatures that didn't match what we see in solar system comets. 3I/ATLAS merges those two stories. It carries the visible structure of a comet, like Borisov, but its behavior echoes Oumuamua. It has a plume, but that plume points toward the sun. It shows acceleration, but in the wrong direction. And its chemistry is baffling. Carbon dioxide levels off the charts, nickel appearing without its usual partner iron, and jets that act less like chaotic dust blowouts and more like steady thrusters.
3I Atlas could leave a tail of blazing dust visible from Earth.
It's also bigger than both predecessors, the largest and brightest interstellar visitor ever detected. Hubble's images confirmed that its teardrop-shaped cocoon of dust dwarfs what was seen with Oumuamua and Borisov, making it far easier to track, but also raising more questions about why it shines the way it does. That's why scientists describe it as a hybrid, the bridge between what we thought we understood and what we clearly don't. We've spent sections dissecting its tail, its chemistry, its motion, its flybys. But what if all of those aren't isolated quirks? What if they're pieces of a larger picture, a plume shaped like a thruster, an acceleration vector that aligns with the plume, not away from the sun, but directly toward it? Propellant chemicals like carbon dioxide and nickel, present in high amounts and capable of being ionized into efficient thrust, and a trajectory so clean it executed 3 planetary flybys with precision that seemed less accidental and more deliberate. What we're looking at isn't just a string of oddities. It's a pattern, a consistent trail of anomalies that points to one unsettling truth. 3I/ATLAS is moving in ways no ordinary comet should. The plume isn't propulsion. Then it represents a process we've never documented before, a force that defies the models we rely on to understand comets. Something natural, perhaps, but still unexplained. And if, against all odds, its behavior does resemble propulsion, then we may have just witnessed an object enter our solar system, change its motion in measurable ways, and continue on its journey. NASA hasn't drawn that conclusion, and most astronomers stress that the anomaly is likely natural. Yet the fact remains. Multiple observatories are still tracking 3I/ATLAS, gathering data frame by frame. Every new spectrum, every new image, is another chance to catch the detail that explains what's really happening. We aren't just looking at the sky anymore. We're watching something move through it, carrying with it a question science hasn't answered yet.